Alright, in this video I'll be doing problems 4 through 8 in the 5.4 homework. So in number 4 you've got this poll, a random sample of adults in some country, we'll just say the USA, was asked when you see an ad emphasizing that a product is made in the USA, are you more likely to buy it, less likely to buy it, or neither? More likely or less likely. The results of the survey by age group are presented in the following contingency table. All right, so it says, what is the probability that a randomly selected individual is at least 55 years of age, given the individual is less likely to buy a product emphasized as made in the USA? So notice it's less likely and at least 55 years old. So basically what we want is the probability of being 55 plus, at least 55 years old, given that they're less likely to buy American or whatever. So notice we're restricting ourselves to the people who are less likely to buy. So less likely, that's this row. There's a total of 67 that are less likely to buy. So we're given that we're dealing with people that are less likely to buy. So the probability that they're 55 and plus, well, they've got to be in that row. And 55 plus, that's 13. So if we divide 13 by 67, you should get 0.194 or 194 thousandths. Now I just want to make this as clear as I can. If you're using the formula, you could also think of it as the number of outcomes in E and F, where E and F are, well, E is being 55 plus and F is being less likely. I guess actually it would be less likely is is 55 plus and E is less likely. And that's divided by the number of elements in, let me make sure I have this right. I guess that would be E. So again, this is basically event E and this is basically event F. So the number of elements in E and F, so people that are 55 and less likely to buy American, that's the 13, divided by the total number of people in the less likely group, which is 67. All right, in fact, let me just go ahead and do this here. This is equal to the number that are 55 plus and less likely divided by the number who are less likely. So that would match it to this problem here. Okay, so that should be good for that one. So the next problem is similar. For part B, it says, what is the probability that a randomly selected individual is less likely to buy a product emphasized as made in America or the USA, given the individual is at least 55 years of age? So this time we're restricting ourselves to those that are 55 years of age. So it's the opposite of what we just did. The probability of being less likely given that they're 55 plus. So this time we're restricting ourselves to the people that are 55 plus. Well, that's this row here. And you can see there's a total, we're limiting ourselves to those 536 individuals who are 55 and over. And we want the ones that are less likely to buy a product. So that was the 13 again. And if you divide here, you get 0.024. And so let me just go ahead and put these in. All right, so that does those, that's for those two. Now look at C, it says, are 18 to 34-year-olds more likely to buy a product? So this is more likely to buy a product emphasized as made in the USA than individuals in general. Well, let's go ahead and look at individuals in general in terms of, are they more likely to buy American? Well, there's a total of 2,168 outcomes, and the ones that are more likely are all of these guys, which adds up to 1318. And here you get 0.608 or 608 thousandths. So what if we restrict ourselves to the 18 to 34-year-old group? So we want the probability that they're more likely, given that they're 18 to 34. So this time we're limiting ourselves to the ones that are 18 to 34. That's this column here. And so 540 is the denominator there for restricting ourselves to that group, age group. And we want the ones that are more likely, that's the 225. And we're going to get 0.417. So you can see generally, overall, the percentage or the ratio is bigger. In this age group, it's only 417 thousandths versus 608 thousandths. So these guys are less likely. All right, so that's the first problem, number 4. Let's move on to number 5. It says, suppose you just received a shipment of 10 televisions. 4 of the televisions are defective. So 4 are defective. We'll use D for defective. And again, there's 10 televisions. If 2 televisions are randomly selected, compute the probability that both televisions work. That's going to be the first part here. And then what is the probability at least one of the TVs or televisions does not work? All right, so first of all, we want to find out the probability that both televisions work. So basically, the opposite of being defective is they work. So we want the probability that they work and work, that the 2 TVs work when we select them. So that's the probability of the first TV working times the probability of the second TV working, given that the first one worked. So the probability that the first TV worked, well, there's 10 total TVs to choose from, and the number that work, well, if there's 4 that work, or I'm sorry, 4 that are defective, that would be 6 that actually work. So 6 out of the 10 work. So that's the probability that the first TV works. Now we're assuming that we've already picked one TV that was not defective, one that worked. So now there's only 9 TVs. And the number that works, since we already picked one that worked, there's only now 5 to choose from. And so if we multiply these together, we get 30 over 90, which is 1/3 or 0.333. So next, it says the probability that at least one of the 2 TVs does not work, or the probability that at least one of the 2 televisions is defective. So I'm going to use D for defective there. All right, so we want to find the probability that at least one TV does not work. Well, there's 3 cases where at least one does not work. We could have 2 that are defective. We could have a defective and one that works. The first TV could be one that works, and the second one could be defective. So we have all of these guys, and then we have the other case, basically the complement, which would be that they both work. So at least one TV does not work, that's these guys, and the complement is these guys here. Now we already know this probability, so let's call this E, and that makes this E complement. It doesn't matter which one you actually call E or E complement, but our formula for the probability of E complement is 1 minus P of E, or the probability of E. So the probability that at least one doesn't work equals 1 minus the probability that both work. So this is EC, or E complement, and this is E. So in our case, we have 1 minus the probability that both work. Well, we already have that probability. It's 0.333. And if you subtract here, you get 0.667, or 667 thousandths. All right, so that's number 5. Let's move on to the number. Now, I'm going to skip 6, and I'll actually do that directly in my math lab. It just makes more sense to do that. So let's go to 7. I think I said I was doing 4 through 8. I'm actually doing 4 through 7 here. Let me make sure I have this right. And we're skipping 6, and we'll do that one last. Okay. So suppose that a computer chip company has just shipped 10,000 computer chips to a computer company. Unfortunately, 50 of the chips are defective. Maybe that's just kind of what they've discovered through trial and error, or I forget what it's called, quality control. So first of all, compute the probability that 2 randomly selected chips are defective using conditional probability. And then part B, the probability that the first randomly selected chip is defective is 50 out of 10,000, or 0.005, which is 0.5%, or basically half a percent. Compute the probability that 2 randomly selected chips are defective under the assumption of independent events. So we'll talk about that in a minute. Let's go ahead and do part A. So first of all, we want to find the probability of a defect. Let's see, 2 randomly selected chips are defective. So defective and defective using conditional probability. Oops, that's supposed to be a D. Well, that's equal to the probability of defective times the probability of defective, given that the first one was defective. So in other words, these two events are not independent, they're dependent. So that would be, well, in the first case, you have 50 to choose from that are defective out of 10,000 total to choose from. So you have a 50 in 10,000 chance that you're going to get a defective chip. Now you've already chosen a defective chip, so now there's only 9,999 to choose from. And since the first one was defective, you now only have 49 to choose from. So if you multiply this out, you get 4 zeros, 0.00002450. In this problem, they want you to round to 8 decimal places. All right. And let's go ahead and put that in. 0.12342450. Now in the second case, they want you to use the assumption of independent events. So what are they talking about there? Well, basically, if the sample is less than 5%, then it really doesn't change the probability significantly to assume that they're independent events. So in this case, we have 2 out of 10,000 chips. and that's 0.0002, which is 0.02%. So we're certainly less than 5%. And so that's why we can assume, that's what we mean by the assumption of independent events. If this sample size is less than 5%, then we can assume independence. Because it really doesn't make much difference in the probabilities that we're going to get, as you'll see. So the probability of D and D, defective and defective, is the probability of defective times the probability of defective. And they told us that was 5 thousandths times 5 thousandths, which is 0.0000. So 4 zeros, 2500. Because we have to round to 8 decimal places. So 0.1234 zeros, 250. And you can see these are pretty close. And so it says when small samples are taken from large populations without replacement, the assumption of independence does not significantly affect the probability. Based on the results, what does this mean? Well, the probabilities are nearly the same. I mean, they're essentially the same. The difference is so small. All right, so that's number 7. So let's go ahead and go to number 6, and I'll go to, oh, am I not going to be able to do this? Let me see if I can do this. There we go. Okay, so it says the following data represent the number of different communication activities used by a random sample of teenagers in a given week. So the number of different communication activities, now I don't know how they're defining that, but you have some that have 0 communication activities, that's this column. Some that have 1 to 2, 3 to 4, and 5 or more. So here it says are the events female and 0 activities independent. Okay, so in this case, if we want to determine if they're independent, we have to find, we have basically a property that says, you know what, let me get some paper and I'll switch to the other screen. This will be a challenge, but we can manage this. So 2 events, E and F, are independent. So we have a test. If P of F, P of F is equal to P, or the probability of F given E. So the probability of F is equal to the probability of F given E. Basically what that's saying is E doesn't affect the probability of F. That's what makes them independent. Or the probability of E is equal to the probability of E given F. So it doesn't matter which order we look at the events. So in our problem, we need to find the probability of female and the probability of female given, and I don't remember, let's see what it was. 0 activities. So the probability of female given 0 activities. So the probability of being female, well, there's 200 females out of a total of 400 people. And so you can find that probability, that's 0.5. Now if we restrict ourselves, well, if we find the probability of female given 0 activities, so this is the column for 0 activities, so we're limiting ourselves to these 44 people, and how many are female? 22. So that's the probability of being female given that you've done 0 activities. And so that's 22 out of 44, and you also get 0.5, and so these two probabilities are equal. I'll show you my work real quick. And so we can say no, or no, I'm sorry, yes. Or wait, are they independent? Yes, because probability of female and the probability of being female given you did 0 activities are the same, or equal. All right. Are the events male and 5 or more activities independent? Well, so here we have to find the probability of being male, and then also the probability of being male given 5+ activities. So let me just show you my screen. So we've got to find the probability of being male and the probability of being male given that we're restricting ourselves to the people with 5+ activities. We want to see if these probabilities are the same. So let's go ahead and check that. So the probability of being male is also 200 out of 400, or 0.5 or 5/10. And the probability of being male given that they did 5 activities, well, there's 105 there that did 5+ activities, and the number that are male are 37 there. Now 37 divided by 105 is not going to be equal. We're not going to get 0.5. And so, let's see, did I do that? I can divide that real quick. 37 divide 105, it's 0.352, so it's definitely smaller. So since these probabilities are not, actually let me switch back. So the probability of being male is 50% basically, or 0.5. The probability of being male given that we're limiting ourselves to 5+ activities is 37 out of 105, or 352,000, so they're not equal. So let's go back. Are they independent? No, because the probability of being male and the probability of being male given you're restricted to 5+ activities are not equal. All right. Are the events 1 to 2 activities and 3 to 4 activities mutually exclusive, or we would say disjoint? In other words, if you randomly choose one person among this group, is it possible that they did 1 to 2 activities and also 3 to 4? Well, no, it's one of each of the, there's 4 possibilities here, and there's no common outcomes. Like, you can't have a person that has 1 to 2 activities and also 3 to 4 activities. And so here we would say, well, it's yes, they are disjoint, because probability of 1 to 2 activities and 3 to 4 activities is 0. So I guess this is actually, we can tell that they're disjoint if the probability of both occurring is a 0. All right, so let's go ahead and check our answer. Are the events female and 1 to 2 activities mutually exclusive? Well, you could be female or male in the 1 to 2 activities group. There's going to be some overlap here. In fact, we can go ahead and find the probability of being female and doing 1 to 2 activities. These are not disjoint events, but we can see it by finding that probability. So it'd be, if they were disjoint, let me go ahead and switch back. if they were disjoint, then the probability of being female and doing 1 to 2 activities would equal the probability of being female times, actually, I'm sorry, we just need to find this probability. The probability of being female times the probability of being female given 1 to 2 activities. So let me go back. So the probability of being female is 200 out of 400. Times the probability of doing 1 to 2 activities. 1 to 2, there's a total of so here 1 to 2 activities, that's 136. That's going to be our denominator since we're restricting ourselves to the ones that are doing 1 to 2 activities, and the ones that are female are 53. So I'll go ahead and switch back so you can see. So obviously if I multiply these, I'm not going to get 0. And so let's switch back. So we would say no, because the probability of being female and doing 1 to 2 activities is not 0. Okay, so that's it for this video. If you have any more questions, just let me know.